probably not the most important thing that has happened in the Haskell ecosystem today. There is now Haskell Ryan Gosling. So there's a
How
whole.
many pictures are there on this?
I don't know.
Oh god.
Too many.
I was hoping it was like 2 or 3, not.
You're like, yeah, yes, that's So anyways, so on that note, well, it used to be a lot more effective, but now it's instantiated.
Maybe cats were a lot less disturbing.
All right. So Paul spent a lot of time talking about what it means to be talking about parametricity at the type level. What I'm going to do is I'm going to play with a lot of parametricity at the kind level. So the type of types. All right. And I want to see what we can get out of rebuilding a lot of the things that we know and love in the world of Haskell a little bit up. So let's see if I can actually close this window. I'll just do it in here. So let's see. You know what? That worked really well for you. So I'm just going to follow your pattern. So let's say that we wanted to talk about categories in Haskell. Okay, we have a class in Haskell for the notion of what's called a category. A category takes some. It has an identity and some notion of composition.
The syntax disable, I'm worried about. The green is very much like the background.
Oh, is it? What's the?
Sin, or that works too. Just SYN and then do off, or space off, and then do sin on again, and it may.
Maybe we could just turn the top.
Oh yeah,
lights
just do
off.
sin on, or that the lights will do.
Maybe we could just turn the front row of lights off.
Yeah, maybe that'll work better because I do kind of want the colors because otherwise it's going to get really hard to read.
You could also just change your color scheme.
Yeah.
I could. What's the?
But that way lies madness.
Yeah. Anyone have a good?
Lucius.
What's the color scheme thing in Vim? This is embarrassing.
Color scheme. With the lights off, I'm getting almost nothing on the screen. I don't know about you. Because having the L, U. Yeah, you can hit tab. Yeah.
It's not tabbing for me.
Oh, all right.
Elf board is a terrible idea.
No, that's a
Oh.
good. Double down on the wrong one here. Before you get too dark, good.
Hey guys.
Hey, before you, does anyone have the bathroom pass that they pocket it?
Yeah, I do.
And could we get those front lights back on? Just for recording?
All right. Keywords are going to fade into the background.
Okay.
Sorry.
We'll disappear like parentheses and types.
Yep. All right, so we have this notion of a category. Okay? And now normally, we have one category that we work with all the time in Haskell, which is the category of Haskell data types, where the identity function is the function that you know and love, and dot is composition of functions. Okay? But one of the things I got them to add in GHC 7.6 was to make the class category polykinded. So there's this notion of polykinds, which if I really have to kind of category. It's going to say, actually, oh god, it's just a terrible variable. Let me pick a better variable. Pick K. Category goes from it takes something that doesn't really care what the kind of its argument is, as long as it ends in star. So these are kind variables, just like we had type variables in all the expressions we were talking about before. So category itself works for anything that takes 2 arguments, no matter what kind they are. Okay? So what should we do with that? We could build something that, we could build another category. We could build a category of natural transformations between f and g. And here we're going to say for all a, I'm going to take an f of a to a g of a. This is the f of a to g of a thing that he was just playing around with.
So just to be clear, for category, should I read home set operator?
This is the hom of a category. We're only going to talk about categories in terms of their arrows. Okay, and we'll eventually talk about a more general setting for this, and we'll talk about enriched category theory by the time we're done. And I'll lose most of the audience by then, so I'm taking it slow. So here, the identity is going to be the natural transfer. It's going to take an identity function. Because f and g will be the same. And we're going to take nat f dot nat g is nat f dot g. I forgot extension. All right, so now we look at the kind of nat. We'll look at the kind of category. Category nat is perfectly happy. We were able to make the instance of category for nat. Nat goes from k to star to k to star. So this k to star is what we call k here. It's unfortunate that page doesn't say very well. But so nat is just like arrow, a level up. So here's a little trick. We can make a type family. Notice I didn't give it any type parameters. So a type family is actually a type level function. In this case, it's a type level function that depends entirely on its kind. We're going to be picking up a few of these. Type families. All right. Might. It's a habit. All right, so now we've got this twiddle, and twiddle looks like both arrow or nat, depending on the kind of the argument that we're interested in working with. So what if I come down here and I change that to a twiddle? Now, I need to be a little more explicit here. So if twiddle is a category for j to star, then nat from I to j to star is also a category. Okay? So what we've done is we've set up a base case for star, and then we've set up something that we can do induction with. So now I to star, I to star, I to j to star, any number of assuming I didn't typo. Oh yeah, I'll actually put parentheses in the right place. Assuming I did that correctly. Flexible contacts.
Flexible instances, flexible context.
I don't think I need flexible instances yet.
You don't need to.
Now I'm gonna switch to the file then. Decidable instances. This is how these start, by the way. All right. Woohoo! All right. So now, GHC chose a really poor way to show nat. It said k to k. But if you actually ask for the kind of nat, it actually figured out that these are different kind variables. Okay? So nat goes from any kind you want to any kind you want to any kind you want to any kind you want. And so now we can use natural transformations of we can build a tower of natural transformations, of levels of universes of natural transformations. You can start playing with fancy infinity-ish category things that I'm not going to bother explaining today. Okay. Anyone who actually knows category theory can help me later, and I'll have to try to put it in more formal context. Or try. Okay. So what we've done is we've built a nice little category worth of natural transformations using parametricity as a proxy for naturality. Now that's actually a lie. There are plenty of things for which this doesn't work, and it's a little bit too strong. So that free theorem thing that, so what is a natural transformation? A natural transformation is something, if you have a natural transformation phi, you have this property for it. Gee, that looks really familiar. You couldn't have set me up better.
You need a dot
Oh!
instead of an equals.
Dot! Okay.
So familiar, we're already seeing this.
Okay, so this guy is exactly what we were talking about just now, right? This is the notion of a natural transformation. It's something that we can move over fmap. Okay?
So, where is your functorality here?
So I haven't,
F and G are unconstrained.
so it turns out that parametricity is stronger than we need. It's really, really strong. It works. This works. This automatically commutes with fmap and contramap.
Well, yeah.
Given their just given.
Assuming they exist.
If they exist, this will just automatically commute. So I'm going to do category theory wrong. Okay, and we're gonna see how far we can go doing a whole bunch of stuff wrong and see if it wraps around to being right again. Okay, that's really the goal of this. Is I sat down and I started playing around with a little library in Haskell, saying, well, what happens if we take the Haskell definition of functor with a capital F, which is always just endofunctors on the category of Haskell data types, and we do it in a slightly more general setting. So we're going to say all of our categories are going to be picked by their kinds. So we're going to have one category that has arguments in a given kind. So we're always going to be talking about categories that look like this twiddle. We're always going to be talking about some type instance of this thing. So it might actually be better if we actually required you to say this. Is that you provide me an H such that H is one of my twiddles. And then I'll say that that's a category. Okay. So what does a functor look like here? So fmap should take a twiddle b and give me f of a twiddle f of b. So now functor works for something that takes something from one kind to a completely different kind. Normally this is limited to star to star. So what does that let us do? That lets us actually sit down and write some functors that, like, you're used to people having to write functor, like, suppose this is left of A, or left of A, right of B, this is right of B. And this should still type check. I didn't bring it either. I'll borrow that from the prelude. Okay, so we wrote an instance of functor for either, just like we would in normal Haskell. But what if I wrote this? This thing that would never type check before. What is either? The kind of either. Either looks like this. Either goes, it takes an argument of kind star, it takes another argument of kind star, and it gives you back an argument, a result of kind star. Okay? So if we look at this a little bit funny, with the parentheses here, this is a functor. From the category with its arguments in star to the category of natural transformations from star to star. Okay? So we can actually build a functor for either, not functor for either A, which is going to take a function and give me back a natural transformation.
This is all going to make Bertrand Russell cry, right?
No.
Really?
Yes. You should be fine. Bertrand Russell will not cry.
Wow.
So this is going to be a natural transformation now. And let's just ask what has to go there.
You might want to turn on.
I don't have to. They're on by default.
Oh, wow. I really should
Now,
learn how things work.
this is going to say, hey, I really need to supply a function from either A1 to either B A1, and I have a function from A to B. Huh. So let's just use it. So I'll use lambda case. Okay, so now I should be able to, if I did this correctly, so what is the type of fmap? Fmap looks like this. What's the type of runnat.fmap? Oh, look, that is fmap over the first argument. We're going to peel out, this was from f of a twiddle f of b, and I'm going to say, remove a nat constructor. This is actually nat in disguise. So remove the nat constructor and put another argument there. This is fac to fbc. So runnat.fmap just got in there and worked over the first argument of either. So we just made functor able to work over any argument in our things. Okay? It's a little bit weird. It's a weird kind of functor. Okay? It doesn't say everything that we can possibly say about functors and category theory, but it says an awful lot of interesting. There's an awful lot of interesting category theory we can say this way. Okay? We can build up the notion of a contravariant functor. So this says you give me a twiddle b, and I'll give you f of b twiddle f of a. So this turns the arrow around. Yep. All right. Okay. So now this is about as far as I think I should go in a building everything from scratch kind of mode. Now I'm going to go through where the heck I can go with this. So I have a little project on GitHub. Uses a few more extensions. Called Hask. And so we colloquially refer to the category of Haskell data types as Hask. Okay? And we kind of pretend that it's just very well behaved. So this HOM is a slightly grown-up version of the twiddle arrow that I had before. So this is I to K. So this is enriched HOMs, if you know what an enriched HOM is in category theory. This is a category enriched over another category. So K could be a completely different category. And that guy's probably K to K star. And most of my HOMs have K equals star. Yes?
Does it need to be a monoidal category?
Well, the category that I'm enriched over has to be, you want to be a nice cosmos, so you have all that monoidal category with all these other things that it has to have. It's a sufficiently nice category.
Right. But you're still working with things that are computable, so it's probably
Yeah. So what I'm going to do is, in general, I'm just going to restrict myself to this twiddle, which is going to restrict me to being enriched over Hask. We're going to be enriched over Haskell data types. Okay, so our categories are going to mostly be boring. And so what do we have? We have the category of functions. We have this category of natural transformations that we just built up. And then I have this other category that I built up before in another project where I showed that the constraint inference system for Haskell forms a category. So what do I mean by that? Okay, so this one's kind of a neat little segue. Let's go back to our little tiny, I lied. I guess I'm going to do one more thing here. So I'm going to make this category of implications. So how the heck can we do this? We can say, I want to make up a data type, dictionary, where dict says, you give me a P, and I will give you. So this is the double arrow that is the. This is like a constraint. This is like eq of a or ord of a or something like that. This is something that's usually passed around implicitly. I want to build up a vocabulary for talking about these things explicitly. So I want to build up a category of constraints. So with the constraint kinds package, or constraint kinds extension, this looks like this. Dict goes from constraint to star. Dict is a functor in our new machinery. We'll actually be able to make an instance of functor for it. And I need to make this colon dash up. So what this is saying A entails B when you can take if given A, I can give you a dictionary for B. Okay? And then we can sit down and say, well, actually, what I really want is that I want to write some kind of weird substitution operator. Let's see if I can do this. This is going to be tough. All right, how's this? So if given that you know A, and if you were given the fact that given B, I can tell you R, and A entails B, then R. How's that? Okay, so what is this? This is saying, well, the first argument is implicit, so we don't actually talk about it here. So I just got my B entails R. And then I have to open up probably doesn't have GATs. Constraint kinds. Yeah, I did need it. It's separate from polygons. Woohoo, type check. Okay, now we have substitution, and now we can define instance, category, this thing where it is, see that type checks. Now I gotta use polygon. I'll never remember this, so it's f.g is sub of. That's left as an exercise for you to understand how that works.
As opposed to the rest of this.
I've explained the rest of it perfectly clearly. All right, so now we have a category worth of constraints, okay? So what does that mean? We can actually write down that foo is the proof that ord A entails eq A. We'll just ask GHC to prove it. When you open up sub here says, all right, I'm going to give you an ord now. Dick says, okay, I use that ord to build an eq. Derp, yes. I probably should tell earlier that, yeah, you can tell me about ord. All right. So we just built a proof that ord entails eq, or ord A entails eq A. And we might have bar, which says that eq of A entails eq of list of A, because there's an instance that tells us this. And we can ask GHC to turn whatever it knows about that instance into another proof. Woo. So now the composition of these two things is that given a dictionary for ord A, I can go give you a dictionary for eq A, use that to build up a dictionary for eq for list of A. So we can compose things that we can say about dictionaries, just like we can compose functions in the category of Haskell data types and stuff. This is an interesting category because it has a little bit less structure than we're used to. And so I'm going to be doing all the things that I do in Haskell. I'm going to turn around and I'm going to do them in this other little funny universe as I can. Okay, so anything that allows me to do them in Haskell data types, I'm also going to do on constraints if I can. And the places where I can't will be, I hope, illuminating. All right, so far so good. So we have our category of functions. We have a category of natural transformations. We have this category of constraints. We have some other ones that we don't really care about, and we have one that I need to automatically enrich things, which we don't really care about either. And then we have special cases going to come up later when I show that we can magically make up some things that shouldn't be able to exist. Okay, so now given a functor, I want to be able to talk about its domain. its codomain. These are just type level functions that are convenient, so I don't have to talk about all these kind variables everywhere. Given an object, I want to talk about what the arrows for that object look like. And then some other stuff that doesn't matter. All right. Okay, and we're often going to work under multiple arguments. So having little convenience functions that let us work 2 arguments in, or 3 arguments in, is kind of handy. And then we can also peel off multiple arguments at the same time. Okay, so this is the category for nap we just talked about. This is the functor that we just talked about. We can borrow the definitions of functor from Haskell if we don't want to write them ourselves, if they're already trivial. And that run.fmap thing. If you know what a bifunctor looks like in Haskell, this is a hint of what I might be building up next. Okay. So now we're going to go down the rabbit hole. Limits. Limits are going to be really hard to talk about in full generality. What I'm going to do is I'm going to work with a very limited form of limit. So what is the lim_c here is something that takes I to constraint, because lim_c is a constraint. This is the notion of limits in the category of constraints. So if anyone knows what a limit is, great. Otherwise, this basically is going to look like a universally quantified constraint. This is for all a, p of a. Okay? It's a fancy way to talk about that in a world where we're not normally allowed to say that. Okay? And so now I'm going to put one hack in. I want to build my house on it. So if given p of any is this magic type that inhabits every kind that GHC gives us. Okay? I'm going to pretend that no one would ever dare write an instance of any for any themselves. Okay? And if you do, I will burn your house down. That is the threat. Okay? And then what I'm going to do is I'm going to use the constraint, p of any to any, the identity constraint. I'm going to coerce it into p of any to a, and I'll let you read it out. Okay? So this guy is the proof that some constraint holds for all a. It's a lie. It's an absolute terrible, terrible, terrible lie, and I'm a bad person.
Has nothing to do with the lie.
Yes. So now, the limit is a functor. So we can map over it. So if you have a limit of f, and you have a function, a natural transformation from f to g, mind you, f is a predicate. It goes from I to constraint. It's a functor into the category of constraints. It's like eq and ord are functors. You get that one through. We can, actually, they're not very well here. No, they're not. But a lot of the ones that we're going to be playing with are. Limit is a nice functor. And so, given this, we can kind of fmap to change out what we're taking the limit over. And then I need to talk about compositions. So I want to talk about composition of functors. Okay? So you're used to maybe the compose functor in Haskell. Something like, new type compose fga is compose of run compose, f of g of a. You might have seen this guy. And it's boring. But if I turn on polykines, I wrote that definition again, and there we go. Now this one looks a little bit more interesting. These guys can be of any kind. This guy can go from anything to anything, just so long as it ends in star. Okay? I want to build things that can go, as long as they end in some category indexed with variables in k, I want this guy to supply me all of those compositions that end in k. And provide me compose and decompose. That's its job. That's the job of this composed class. We'll make an instance of composed for basically the Haskell era, the hum for Hask. We'll also build them for other interesting places. And then we'll make an infix dot, because why not? Because, anytime things get complex, you throw Unicode in just to scare away anyone who So what we're going to do is we're going to build this guy. So we're going to build compose in the category of constraints. You give me this is f of g of a. This is the definition that we wrote in the category of Haskell data types. So this is f of g of a is the definition of composition that end in the category of constraints. And here's the definition. Compose is subdict. Go get your superclass.
So overall in Haskell is
Yeah, all we're doing is
of colon hyphen.
yes, colon dash is just ask Haskell to do all the work for us. Okay? So we're just going to ask the type checker to do all the work to prove that you can compose and decompose functors that end in, or a functor that ends in Haskell. Now, we're going to make one horrible looking definition. So the limit of taking a composition that ends in the category of constraints is what we're going to call post. So I'm not actually going to expect you to get this one from my explanation. What I am going to say is that if we look at what it does, we can actually get a sense for how it's used. All right. So here, fmap1 says you give me a post functor for p, and I'll give you given an a to it'll b, I'll give you a PCA to PCB. This is a functor in its second argument. We use the limits to skip over the first argument.
Post compose.
Yes.
Okay.
So this is so post functor lets you work one argument out from p. Okay. And this is natural in C. That's what post functor required, was that we work as a functor in the second argument independently of the first one. So we can build post functor and go 2 arguments out if we want. We can build contramap 1 argument out. So why does this matter? Why the heck do we bother? Well, if I do this, now I don't have to make the notion of a functor in my second argument as a separate class. I don't have to remember to put functor1 instances in my code everywhere. I write the definitions for functor for the first for the arguments as they're needed. And then what I can do is I can come down here and say that a bifunctor is just something that's a functor in its first argument and is also a post functor. It's a functor in its second argument naturally with respect to the first. Okay, and we use parametricity as a really strong form of naturality that ensures that we're natural in both arguments. So, okay, how's that for getting interesting?
What do monads look like in our regular world?
Eventually, they will be monoids in the category of endofunctors. I was hoping to get there. It's not quite there yet. You actually have to build them up explicitly. But as soon as I actually have proper monoidal functors so that the category theorists in the room do not yell at me, then I will be able to say exactly that. Okay? So, that was going to be the punchline today. I didn't quite get there. I got tied up trying to get something else done working last time. Okay. So we've got bifunctors, we've got bimap. So I've been explicitly not talking about the category. Functor doesn't actually have a constraint that is coming from and going to a category. And that's actually that's an artificial limitation that I'm putting on myself. And the reason is because I want type inference to work a little bit better. Because I want to not have to pick which category I'm coming from when I have something like the constant functor that doesn't care what category you're indexing over. Okay, if you don't use the arrows over there, I shouldn't have to know that it's a category. And so I move the uses of the category constraint to the use size, which is something we love to do in Haskell. I'm just doing it a little more generally. All right. So we have this notion of a bifunctor. It's just a functor in its first argument. It's a functor in its second argument. And because this is basically a functor from where we started to the category of natural transformations, and this is just a normal functor, but it's what I do that. And it doesn't really matter the order that we map these two things. We just have to do them. All right. And then, for those of you who've been following Lens, we have this notion of a profunctor. And a profunctor, if you actually know what a profunctor is in category theory, this would actually be a distributor or a it's the opposite category of the normal categorical presentation of a profunctor, because we want it to line up with the argument order of hop. Okay. And so this is a functor that is contravariant in its first argument and covariant in its second. And these are, also for the categorically inclined, these are enriched profunctors. So we have a profunctor, and it has to be going to some interesting category. So you're going to say, you give me an A twiddle B and a B twiddle C, and I'll give you a PD C or PAD. So you can pull backwards on the first argument and push forwards on the second.
Where did LMAP happen?
Huh? LMAP is runmat.contramap.
Okay. I believe it exists. I just didn't see the name.
Yeah, we kind of ran past it
I believe
quickly. There we go. Run that contramap, just like first was run that fmap. Because first is to indicate, hey, look, it kind of sounds like bifunctors methods.
Clearly, you were going to make arrows.
Yeah, actually, I do eventually. They're just any strong profunctor that is also a category. There's a definition
You
line
do
around.
strong?
Huh?
You do strong?
I might get strong. We'll see. I don't think I'll actually care about any of the lens machine. So now, if you've been using lens, we're going to do category theory with lenses. Okay? So in lens, we have this definition of like, how many people here have used lens or looked at lens? All right, so maybe a third. So in lens, what we would say is instead of talking about it like an isomorphism, we would talk about an isomorphism family, which would basically be a lot like talking about a natural isomorphism. Except I don't have the vocabulary to say that correctly in Haskell. So what I actually have to do is pick two instantiations of a schema that I'm coming from and two instantiations of the schema that one I'm going to, and basically say, you give me any profunctor, P, and I'll take PAB, yes. So this would be, this would have to be, you gave me some way to get from S to A, and some way to get from B to T. Why? Because by parametricity, I have no other way to manipulate P other than through dymap, basically. I could fmap over the first argument, or I can fmap over the second argument, I can contramap over the first argument, but any number of compositions of those is equivalent to calling dymap once with the right composed functions. So this is effectively calling dymap with two arguments. Any ISO looks like that. Oh, shit. So we're going to be using this as sort of a slightly generalized isomorphism, where the types don't have to exactly line up when we come back. So we can talk about the notion of an adjunction.
Just that you get hyphen dash. That's all I care.
That is why I have it. So you have a class named by this symbol, and this symbol is used because it is exactly the symbol that we use in category theory. Well, modulus unity. So this is that F is left adjunct to U, and F determines U, and U determines F, when there's an isomorphism between arrows from F of A to B and A to U of B. Okay? And when we come back, we're going to allow you to swap out A's and B's for slightly different things. Okay? That is what an adjunction is in category theory. Now, this is a natural isomorphism. It is natural in the arguments A and B, etc. But
That's adorable.
that is an adjunction. And now we can talk about the unit and co-unit of the adjunction. We can talk about all sorts of fancy things. We can talk about properties of all right adjoints, all left adjoints, etc. that don't matter. Okay. We can borrow more structure. We can talk about the constant functor. So we talked about the limit functor, but we didn't actually say what limits mean. But now that we have adjunctions, we can. So we can say that the constant functor is going to go from, say, star to natural transformations from I to star, basically. But in this case, from a category to natural transformations that end in that category. We're going to go from C to C to the J. Would be the way category text would say this. Right? In this case, J to J to the I. Where I is some index category. And you've got some small criteria that I'm skipping completely because they're all going to trivially be satisfied because we live in SET. We live in Hask. Huh?
Countable.
Yeah.
It's really small.
We're going to live in a very nice place. Okay. So we have the constant functor we're going to have this little const isomorphism, which says that we can put on and take off this KD thing. And then we'll build instances of this schema. This is where I'm finally forced to say, oh man, my induction just doesn't work for me by magic anymore. I have to actually write one of these const things for every j that I care about. Okay, so I'm going to make const1. This is the normal const functor that Paul used in his talk earlier even. Well, it's polykind in A, right? This has to work for all I. It's the same const functor with polykind. And then we're going to use dymap to take off or put on the const constructor. So dymap is the way that we talk about the isomorphism between those two halves. You give me what you want to do to get from there and there. Or to get from here to here and then from here back. So this is the bit that'd be really weird to people who are just used to category theory and not used to lens. If you're used to lens, this would basically be the iso function that we have in lens. You give the two halves. And now we can say that const is a functor, and that const applied to one argument is a functor. And normally you'd want this to be a contravariant functor, and so on. And like you want to go to a contravariant, to the constant category. That we don't actually care here, because the variance is going to be oblivious to whatever coming from the opposite category diagram or not. And so we're a functor. For const, we are both a functor and contravariant, which means we basically can't use that argument in the second argument. Okay, and that's the sort of conceit of lens is that we can use that to talk about the unit category. So we can talk about what a semi-monoidal functor is. Well, actually, we don't talk about that. We just make a whole bunch of instances out of order. Oops. We can talk about more things about const universe up. We can talk about the constant functors of the category of natural transformations, or from the category of natural transformations to the category of natural transformations with an extra argument. This is going from j to star to I to j to star. But what is interesting about the constant functor? Well, let's get to limits. Come on. Oh, we need one more. We need a constant functor that ends in the category of constraints. So you make a class named const, and you drop it in the same thing. So you're not used to probably talking about data types and making them instances of something, and then just turning around and making a class also an instance. But it works out. The kinds check. Perfectly legal. And the nice thing about it is this definition didn't change. The body of functor for const C is the same body for all of these things. If we actually had the ability to make data families that, like, we could change the kind of the last argument to allow that last argument to be polykinded and move the constraint that it has to be instantiated to star in the last argument to the instantiation site, and then maybe we have the idea of a class instance. We could actually totally just use data families and some things and write all of my instances for these things once. Which actually kind of neat. I don't have that. Okay, so const to the functor category, or to the category of constraints, is also a perfectly legitimate const. And let's get to something else interesting. Category of natural transformations to constraints. You can see it's a little repetitive. All right, so now we can talk about what it means to have a limit. So in Haskell, the way we take limits, the easiest way to take limits is just to talk about things that are universally modified. We use parametricity to stand in for naturality in all the right places. Okay, so limits that end in Hask, end in star, look like this for all x, f of x. So this goes from I to star to star. Lim is a functor, and it's all sorts of fancy. But when we finally get down to it, we can talk about that adjunction. That was the whole point of what I was rambling on about. I needed the constant functor to talk about what it means for the limit to be negative. So what the heck are we saying here? We're saying that if you give me, this is the same as giving me, so what do we know? We know that const 1 takes a, let's call it I, or let's do star, I to star. we know that lim is going to go from I to star to star. These are actually J's, but. So adjoint functors kind of go between categories in the opposite direction. So we're going from I to J here to J, and we're going from J to I to J. So they're going in the right directions to possibly be adjoints. So what is this saying? This is saying that if you gave me a function here, what would this be if we expanded this? So if we ran that, you're going to get a function from the constant functor. This is just an A. For all B, and then you pull this over here, and then you make that a lim. So this is going back and forth between these two representations is what this adjunction proves, is that if you have a natural transformation that ignores its argument, or you have a mapping that works for all arguments, you didn't really gain or lose any information. These two things are the equivalent. Okay. And then all sorts of fancy boilerplate of putting on and taking off natural transformations to get in here and out of there. But all I'm doing is just plumbing the arguments around. And I do the only thing that works. Okay. So we just built limit is right adjoint to const. So that lets me move between talking about limits to talking about the constant functors, which are much more easily manipulated than I can. So if I have something that ends in a limit, I can pull it over, pull the mass of everything over to the left-hand side of the arrow, manipulate it as a constant. What else can we do? Oh, we can talk about a category being complete. So a complete category has all small limits. So what we have is the category with objects in J, and this must be some hum. So this is just me forcing this to be a twiddle. Says that we can eliminate our limit of G can give us a G of A. We have a.
That's why you're on the first one.
Huh.
You live.
Yes. Yes. So we have to eliminate limit. And then complete says that there's a proof that const is left adjoint to lim for all choices of I. Okay, and we don't have anything big enough to not have that whole little block. And so there's our proof. So there's the proof that in some sense Haskell has all small limits. Now, this is a lie because my limits are slightly limited. And we can have some other categories that have limits as well. But this one is interesting. Having limits for constraints means that we can talk about universally quantified things. You want something to be a monoid, like M of A should be a monoid for all A, or something like that, which is something that people have wanted to say for a long time in various places. Now you can just talk about lim of monoid. Continuous functors. Absolutely. But what is really nice to me is that all the code that I write for Hask, if I write it using the right machinery, using all these ISOs and things like that, it's actually really easy for me to lift up all of that code and just talk about it at the constraint level. So we talk about lenses into star all the time. Now we can talk about lenses into other kinds, right? We can talk about lenses that work with natural transformations, or traversals that work with natural transformations. We can talk about lenses into constraints. You can actually go through and work with a constraint that is a pair and go manipulate the first half of that pair with a lens, which is kind of cool. Come on. What else do we have?
Do you do the normal, everyone's favorite limits as limits?
Limits are.
Do you do like product as?
I do not yet.
Yeah.
I'm currently choosing to use product with comma and then lifting comma automatically into the category of natural constraints, which
Or
is cheap.
pullbacks or
Yeah, I don't.
take a mic.
I do want to do. I do want to do
example of
equalizers and co-equalizers because I do have co-limits as well.
Right.
Although I don't have co-limits in the category of constraints yet. Those unfortunately don't work out.
Yeah, or it's hard.
So then we have this lovely type. So this is the thing that lets me. So if we ignore this type, which is the kind of this is god awful. It's probably the worst kind of signature I've ever written. We can say that lifting should be able to take kind of any bifunctor-like thing and two functor-like things and apply it. So what I want to be able to do is I want to be able to borrow comma. I want to be able to borrow pair from Haskell. I want to be able to borrow either and use it to talk about functor products and functor products. I want to talk about a universality. And there we did. So that is awful, but the implementation is trivial. Right? And it's a functor, and it's its first argument, it's contravariant, and its arguments of its contravariant, post, functor, all the right things. We can lift into the category of constraints. So if we have something that works on constraint, like an and or something like that, then we can work with I to constraint. We can do the sort of functor product, functor co-product for our functors that live in the category of constraints. All right, where the heck can I go with this? Let's see. So what this nicely gives me is sort of a free lifting of all of the Cartesian structure of Hask to nat and to nat of nat and to nat of nat of nat. We can keep borrowing the Cartesian structure all the way up the tower.
Do you have a class that has like curry?
Yes, we're going to do curry. Okay, and so we need a notion of product because we can't talk about comma unless it's fully saturated in the category of constraints, so we have to build our own comma. And let's get to something interesting. There's a bunch of machinery, so I can actually recover. This is a bunch of lens plumbing. There is something interesting here. The Untitled lemma shows up.
Really?
Yes. We use it all the time in lens apparently. So the way that we read from a lens is we use the Untitled lemma, or the Untitled embedding, and we see where it sends identity. That should sound really familiar. So what is this? Get says, I'm going to take, you give me an object R, right? And I'm going to give you some, so R is a member of my category C, and I'm going to give you basically all of the HOMs that end in that object R. I should look like Unita. All we've done is we had to bolt in this funny little I here to make this thing look like a profunctor so that we can work with this in the category. But other than that, this is Unita expressed as a functor from the normal, from cat to prof. So it's Unita in a funny little way. But the way that we read from a lens is to use the Untitled lemma. We just ask where it sends the identities. The way that we build backwards with a lens is to use the opposite form of the Untitled lemma that puts it, picks a contravariant argument and goes from C out to C. So if that means anything to anyone in the audience, great. If not, don't worry about it. And then we can turn our isomorphisms around with this un thing. And all this plumbing is the same code that we have in Lens, a little bit simplified, actually, which is kind of fun. But now it's enriched in such a way that it can work over any category that we want to work with, which I think is really kind of nice. So we can, so where this becomes useful, and where I originally started playing with this was, if I want to work with like a syntax tree, a really complicated syntax tree like JMacro, where Gershon was talking about that last week, he often has things where like the JMacro syntax trees have statements and expressions and all these different types of things. And when you're working with that, you want to take statements to statements and expressions to expressions. You need to preserve that information, that extra structure. That's naturality. So if you work in the category of natural transformations and you're working on a G80T that has those constraints on it, it just does the right thing. And so you can build a traversal that goes in and lets you take expressions to expressions of the same type, or that lets you take expressions to expressions and statements to statements. Okay? And it's all the same plumbing. So all the standard lens combinators just work there. When we get done with this, if I rambled on for another hour, we could actually get to the point where we can talk about monads, where monads are now parameterized by an extra argument, and we can borrow Conor McBride's construction for Clisely arrows of outrageous fortune, and we can use that to build index monads and indexed comonads and all sorts of fancy things that we've talked about, that people have talked about before, in this formalism using the existing classes. But it's still using return. I didn't have to make up new names for it. Everything just works. It's just in a different universe. Or a different kind.
Do you end up doing return equals whatever you named Ada?
Return winds up a little bit
pretty
more.
cool.
Actually, return is implemented as a derived thing. There's the definition of return. Obviously. So this guy is, you give me a monoidal functor. So this works, return is pure, really. Given any monoidal functor, this has to be a monoidal endofunctor because we need it to be strong. We need to be working, this is actually a Cartesian functor because we're working over Cartesian closed category. And we need some other constraints because we want this notion of tensoring so that we can talk about some other fancy stuff. But when you're done, you can hit return and you get join.
Isn't that much stronger than zero?
No. No, actually, this is every functor in Haskell from star to star is strong. Monoidal functors. Hask is a CCC, and this is trivial for. No, this guy here is like literally the trivial constraint. It has no. It turns into no constraint. I didn't mean this whole construction is trivial. This whole construction took me like 3 days. But we can build up the notion of a comonad, and it looks pretty recognizable. You have extract and extend, and all of the parts look like you would expect in Haskell. We can build up product categories and all sorts of things. So anyways, I'm not sure that the point of this is that you should do this. The only point of this is that you can do this.
We do what we must because we can.
And the only real reason I started playing with this was because people have asked me, well, what do working with pure profunctor styles of lenses and stuff like that win for you? Okay. And for me, what it's really won here is it's won a common vocabulary that I can use when I'm switching between all of these different universes. All of these different worlds where I'm working with constraints in one case, where I've only got like a Cartesian-like structure, and I'm working with types and star in another place, and I'm working with natural transformations in another place. And I'm able to use all the same vocabulary between these things. And I'll do one last thing, and we'll wrap up. I realize I'm running long. Oh, come on. Very curried. All right. No class name curried. Here it is. This is a... shrinking my font size until I can read it anymore. Okay, so curried is a really fancy form of adjunction. Okay, and it's the adjunction that actually everyone uses in category theory all over the place. It's the prod hum adjunction, internal hum adjunction that holds for Cartesian categories. Okay, so what is this? This is saying that normally we didn't have this second argument here. What we're going to deal with is we're going to say we can take kind of product-like things on this side and turn them into arrow-like things on this side. Okay. And when we do that, the A and the B and the C all stay in order. Okay. Intuitively, that's what this means. Is I can move forward and I can move backwards. I can pull arrow-like things back into product-like things. Okay. That's the bones of a Cartesian closed category kind of look like that. You know, like we use this under lots of things that are not CCCs. But so the common example is that we take products to the exponential object in the category, the internal hum, or functions, basically. A cooler example is that we can do this with function composition. On this side, we can get the right con extension over here. And it's curry. Okay? You use the curry function to go from composition of functors to icon extension. We can take profunctors, and we can talk about the notion of profunctor composition over here. And we can take sectioning it on the right, which turns out to be right, this currying adjunction over there. We can take copowers over here, and we can turn them into the internal hum, or the enriched hum of a category. We can move back and forth between all these different notions. And now, most of these things are things that I realize that 98% of the audience here has never even heard of, but it's really freaking convenient that they all drop out and become the same thing, because it's really tedious to talk about them all individually. And really, I think that ability that things that feel the same just become the same when you play with the vocabulary of the problem enough is really the power of Haskell. This is a nice little exercise in saying, well, if I just write down all the things, and I don't try to collapse them down and make them all the same, if I don't try to generalize as early as possible, I just use parametricity. I just take all the free things that parametricity tells me. Right? I don't even have to write down this kind signature. This is for me. Okay. If I just take what comes for free, then Haskell gives me these sort of magical refactoring powers. Parametricity just makes it really easy. If I take one program that worked and I turn it into another program that still compiles, it should just work. If I didn't do anything that did anything with the hard computational bits, okay. And so this thing started out with something completely different, completely different sets of abstractions underneath the hood. And we swapped them out 8 different times trying to find the right way to talk about this stuff. And the fact that we could is really what keeps me programming in Haskell. All right. And so if you take nothing else away, that's about it. So that's what I've got. So, any other questions?
In the first minute.
I can switch back to the types file. Oh yeah. We have the kiddie pool version.